Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And here we're going to look at how to estimate the error variance of the model. So here the model is y equals x beta plus epsilon. And it's the standard assumptions. The mean is 0, constant variance sigma squared, covariances are 0. X is n by p with rank less than p. Call it R. And the goal of this video is to estimate sigma squared. Now, as a reminder, the estimation space is this, or the piece of the model that we estimate, x beta. We estimate it with x beta tilde, where this is the least squares estimate. And we've shown in a video, least squares estimator of beta, that it has this form and must equal my, where m is the perpendicular projection matrix on the column space of x. Now beta is not unique, but x times beta tilde is unique. And we proved it all in this video. Now the error space, and what we're interested in, is an estimate of the epsilon. We call it E. And it's y minus x beta tilde. So this is, how far off we missed the predicting y. Now, beta, of course, is the least squares estimate of beta, the parameter beta. And so if we plug in what we know here, it's this, which is my, right, from the previous video. We can factor out a y, and we get I minus my. And this totally makes sense because here, the estimation space is my. M is the perpendicular projection matrix on the column space of x. And I minus m is the perpendicular projection matrix orthogonal to the column space of x. And so it's the error space. So the E is also unique, right? Everything in here is unique, even though beta tilde is not. Now, the unbiased estimate of sigma squared, we're going to use this video, mean, variance, and covariance of quadratic forms. And the formula is this, where A is symmetric, and we go into great detail how to derive it in this video. Now, for the model above, the mean of y is x beta, and the variance is sigma squared I. So now, to estimate the error variance, we look at the sum of squared errors, and we plug in what we know for E here and here. We take the transpose in, and then we get y transpose I minus m transpose I minus m y, but I minus m is symmetric, so the tick doesn't matter. It's also idempotent, so we get it back. So we ultimately get this expression here. Now we can use this video and the formula in the video, and it becomes the trace of I minus m sigma squared I plus this. Now one note though is this quantity here, I minus m, is a perpendicular projection matrix onto the orthogonal complement of the column space of x. So if we take x times it, this makes it 0, because this is in the column space of x, and the only way to be in the orthogonal complement space is if it's the 0 vector. So this is 0. So what's left now, the constant we can take out front, and the trace we can just take the trace of each matrix. This is the identity matrix, so that's n, and the trace of m is whatever the rank of x is. And I'm going to point you to a video we put out called Projection Matrix onto the column space of x. It's in this playlist, General Linear Models, Design of Experiments, and we called the rank of x R. So now if we take the expected value of this and get sigma squared times a constant, if we divide both sides times n minus r, then that becomes an unbiased estimate for sigma squared. So thus, this quantity is an unbiased estimate for sigma squared. Now let's look at the distribution of the quadratic form divided by sigma squared. And here I'm going to point you to Theorem 6 in a video that I call Distribution of Quadratic Forms Part 3. Y is multivariate normal, x beta, sigma squared I. So then we can take out this sigma squared and then divide it over and we get this. And then that is multivariate normal with mean 1 over sigma x beta I. And then it fits into this theorem a little bit better. I have other theorems to handle this case, but this is easier to see. So note that I minus m is symmetric and idempotent with rank n minus r. Then the theorem tells us this quantity is a non-central chi-square distribution with this rank, this degrees of freedom, and the non-centrality parameter lambda. But as we pointed out, I minus mx is 0. So the non-centrality parameter is 0. And we get this quadratic form is a central chi-squared. Now note that this video will be absolutely critical in the development of hypothesis tests and confidence intervals. Well, that's all I have for this video. Hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.